Today in renewable energy engineering, solar, wind and biomass energy systems, we are going to see last lecture of wind energy system. In last week, we had wind energy basics and concepts. In that, we spent almost lecture 1 and 2 on turbine terms, types and theories, which included all these topics. In this week of characteristics and power generation from wind energy, first lecture we could cover till wind data, because we took bit of time to recap whatever we have done in last week with some additional information. So, today in this continuation of characteristics and power generation from wind energy, so we would be covering airfoils and general concepts of aerodynamics, general terminology used in wind speed estimation, formula for velocity probability distribution, torque at maximum efficiency, wind tunnel performance parameters. In all these things, to explain the concept better, we would be doing parallelly practice problems. Apart from these practice problems, Professor Goud, who is my co-instructor of this course, would also be covering few practice problems on same characteristics and power generation from wind energy. With these two lectures, we would be concluding this week. This is probably 8th week of this course, and then you would be having almost 2 weeks for your final exam. So, if we see whatever we have done in the last lecture, we reviewed extensively what we have done in last week, and then we introduced certain extra additional information, which is nothing but solidity. And here we had seen the formula for solidity, which is nothing but blade area upon swept frontal area. So, you might be wondering how it came as NC upon pi r, right. So, this is nothing but blade area upon frontal area. So, even if you see the blade area, this n is number of blades. So, C into span, right, chord length into span, and if you are seeing this one, this is pi r into r, pi r square, right. So, since you have assumed that blade length is nothing but the tip radius, so this both are same. So, what you finally get is NC upon pi r. So, this I just wanted to tell you like how it derived. As I already mentioned, we are not going in depth of wind turbine design and how we arrive at certain formulas. Since it is an introductory course, we are taking directly the formulas and calculating certain parameters, but if you are exclusively taking a wind energy course, you would be knowing what is the basis of all these things, right. And also I might probably told you that Cp, which is nothing but power coefficient, so that also can be done from certain correlations. So, in that one thing I forgot to mention here, when you are explaining this epsilon, which is nothing but CD upon CL, drag coefficient upon lift coefficient. So, this is valid when only lambda is greater than 1. So, that limit is also there. Anyway, this two formulas would be covered or would be used for certain practice problems by Professor Goud. He also would explain you over there, but this also one should remember, like what is the applicability, because these kind of information I would have told you in my very first lecture of solar energy. When you are using certain correlations, so you should be making sure that, so those constants, right. So, those were fitted constants. So, you should be very careful about the applicability of those correlations and whether any certain assumptions being made, right. For example, here if you want to do it for propeller type rotors, or if you want to do it for multi-blade rotor types, then your epsilon may not be similar, right. So, such kind of information one should be careful about before using any certain type of correlations. And then we covered about the wind data. So, how one would be collecting and how to represent them in a feasible manner or reasonable manner. So, that also we had seen. So, today we will start with airfoils. In airfoils, lift force and drag force I already explained you. So, lift force is nothing but perpendicular to direction of the oncoming airflow, and this is also consequences of unequal pressure on the upper and lower airfoil surfaces. Opposite to that, drag force is nothing but parallel to the direction of the incoming airflow, and drag force is due to both viscous friction forces at the surface of the airfoil as well as due to unequal pressure on the airfoil surfaces facing toward and away from the oncoming flow. Pitching moment is something like defined to be an axis perpendicular to the airfoil cross section. So, if you have a airfoil something like this, so you would be having the lift force in this direction and this would be your drag. So, pitching moment is nothing but this way, right. This is pitching moment, which is about an axis perpendicular to the airfoil cross section. And then this lift coefficient, drag coefficient, pitching moment coefficient, everything we already defined. But however, if you want to consider them in terms of chord length and span, then you can define in that way as well. So, I probably might have told you FL upon of rho u square A. So, this A is replaced by C into L, right. So, what is C? C is nothing but airfoil chord length, L is nothing but airfoil span. So, this airfoil span also I explained you here, span and chord I explained you. So, if you substitute area as C into L, so this C is given here and L is taken over there. So, that is why it is just like the way of representing it, right. So, lift force per unit length upon dynamic force upon unit length. Okay. So, rho u square C, that is why chord length and this is span. So, the same way drag force upon unit length total divided by dynamic force upon unit length. So, this is again rho u square C, the L is taken above. Pitching moment is the pitching moment upon dynamic moment. So, rho u square A into C, right. And rho is nothing but density of air, u is velocity of undisturbed airflow or free stream velocity. I have already told you some author use u in reference, I already told manual uses u, and in Suhatmi's book it is represented as V infinity, both represents the free stream velocity. A is the projector airfoil area which is chord into span, and C is the airfoil chord length and L is the airfoil span. And then the general terminology used in wind speed estimation. So, in the introductory classes I have told you about this power law profile. The power law represents a simple model for the metrical wind speed profile. The basic form is what I might have told you is V upon V naught, which is equivalent to H upon H naught power alpha. So, the alpha is nothing but power law exponent, or we can say it as a surface roughness coefficient, and u at z, zr, zr is equivalent to h and h naught. Z is the particular kite with which we want wind speed, and zr is equivalent to h naught, which is nothing but some reference height at which wind speed is known, and u at zr is already known at reference height, u at z is supposed to be found out. So, this is simple power law profile, and apart from that there is a logarithmic wind profile. So, which is nothing but u of z is equivalent to u star upon k ln of z upon z naught. U is here the velocity which is to be found out, u star is nothing but root of tau naught upon rho, tau naught is nothing but surface shear stress value, and rho is nothing but the density of the air. So, if you substitute u star, then what is left with is k, k is von Karman's constant. So, these are all comes from fluid dynamics or fluid mechanics. You are requested to refer any standard fluid mechanics book. As I told, here we are defining as well as using certain formulas to find out parameters required, but we are not going in depth and how to derive such formulas, since it is a introductory 4 lectures of 2 weeks course on wind energy. Because if some of you are not working in mechanical or chemical engineering or energy engineering, so you might have not had this particular course on fluid mechanics, it would be very difficult for you to get these terminologies, right. So, you can take any good online help, or you can refer certain books on fluid mechanics to get to know in depth about these shear stress value, von Karman's constant, etc. So, K is von Karman's constant, Z is nothing but that at particular height, and Z naught is nothing but surface roughness length. For values of surface roughness length for various types of terrain is given here, Z naught, which is in mm. So, based on the terrain types, you can have Z naught. So, using Z naught, K, and then U star, one can find out U of Z. So, that is nothing but this is ln of natural logarithm of Z upon Z naught, which is nothing but U of Z K upon U star. So, this is ln Z upon Z naught, which is nothing but ln Z minus ln Z naught. So, if ln Z naught you want to calculate, so this particular term plus ln of Z naught, right, y equal to mx plus c form. So, from that also one can find out Z by graphical as well as by a pen and paper, right. Apart from that, there is a air density calculation at 1 atmosphere and temperature of 15 degree centigrade. So, which is equivalent to 288 Kelvin. So, we already know the ideal gas law, P v equal to nRT. So, P v equal to nRT, P by RT is equivalent to N upon V. So, N is nothing but number of moles per volume. So, we call this as a molar density. So, again the mole is defined as mass upon molecular weight. So, if you want to convert into mass, then moles should be multiplied with molecular weight of the air, right. Then number of moles into molecular weight is mass, mass upon volume is density. So, that is P m upon R T, right. And another one here is the P is given, right. So, P is given 1.01325 into 10 to the power of 5 Pascal, which is nothing but Newton per meter square, into m, that is 28.97. The unit is kg upon kilo mole. R if I substitute 8.314 kilojoules per kilo mole Kelvin. For T, if I substitute 288 Kelvin. So, Kelvin get it cancelled, kilomole kilomole. So, here we have kilojoules and here we have kilogram. So, this Newton meter, 1 Newton meter is 1 joule, right, the force into distance. So, if I multiply with meter above and below, so this will go, right. So, this is nothing but kilogram per meter cube and 1 K is here, right. So, if you do this, then what you would be getting is 1.226 kilograms per meter cube, right. Or if you do not want, then here itself you can substitute that 314 kilojoules per kilo mole Kelvin, right. So, if you want to convert mole into mass, kilojoules per kg Kelvin, because that whatever we substituted here as a 287 is in kilojoules per kg Kelvin, right. So, one can directly substitute this way, or you can substitute and do the manipulations and get rho as 1.226 kg per meter cube. So, that is all about the air density at reference pressure of 1.01325 into 10 to the power of 5 Pascal at T at 288 Kelvin, which is nothing but 15 degree centigrade. So, the next one is formula for velocity probability distribution. So, this is the Rayleigh distribution is the simplest velocity probability distribution to represent the wind resource, since it requires only the knowledge of mean wind speed. So, if you see probability distribution function pi upon 2 u upon u bar square exponential minus pi by 4 u upon u bar whole square. So, this some books refer as small f v, right. So, the u and v can be interchangeably used. So, this probability density function and cumulative distribution function is capital F of u or f of v, which is equivalent to 1 minus exponential minus pi by 4 u upon u bar whole square. And Weibull distribution I already told. So, based on certain comparison between experimental data and other statistical models, Weibull distribution function is almost accurately matching with the existing experimental data. Use of probability density function requires knowledge of two parameters, one is shape factor and scale factor. K is Weibull shape factor, C is Weibull scale factor. So, this is also P of u probability density function is nothing but k upon c u upon c power k minus 1 exponential minus u upon c to the power k, and the cumulative distribution function f of u is nothing but 1 minus exponential minus u upon c k. I probably used instead of u v. So, this is followed by Suhatme's book. Okay. And then the average wind mission power P w bar can be expressed as P w bar, which is equivalent to rho of 2 by 3 d whole square u bar cube. So, P w bar is nothing but average wind mission power and u bar is average wind velocity. So, if you multiply this with 8760 hours will yield an expected annual production. So, how we arrived at 8760 I already explained you. So, where from this particular formula comes is nothing but that P w bar is nothing but function of P of v, that is probability distribution function PDF, and then it is a function of P w at u. So, this is nothing but the known turbine characteristic curve, known turbine power curve, right. So, if you want to write P w bar, which is 0 to infinity P w at u, that is characteristic curve, power characteristic curve, and P of v into dv. So, we already know that P w u or v, suppose I will use u only, so that you will not get confused, P u, right. So, P w at u can be written as P a eta and then C p. C p is power coefficient, eta is efficiency, and P a is nothing but actual power. So, this can be written as half rho a u cube C p eta. So, if you go and substitute here in the P w bar, so you can take it out, half rho a can be referred as pi r square and eta, right, and then C p lambda, because as a function of lambda I already given you correlations formula. So, then u cube and then P of u du, right. So, if you want to calculate at maximum, then you can substitute C p as a Betz limit. So, then P w bar is nothing but half rho pi r square, and if you take eta as 1 for ideal, because we are considering C p Betz limit, C p Betz, then what you would get is u cube P of u du, right. If this integral between 0 to infinity is calculated, then what you would be finally arriving is P w bar, which is equivalent to rho 2 by 3 d whole square into u cube. So, this is called a Rayleigh Betz limit, why Rayleigh-Betts limit? So, we already know this probability distribution function. You can substitute it either from Webel distribution or from Rayleigh distribution. So, if you substitute this P of u probability distribution function from Rayleigh, then you would be arriving this formula Rayleigh-Betts limit. So, this was done by a researcher called Carlin in 1997. He called it as a 1, 2, 3 equation, because the density is raised to power 1 and 2 by 3 d is raised to power 2 and u bar is raised to power 3. So, that is the equation we would be using to calculate the average power produced, right. Otherwise, this is when you substitute this probability distribution function and then you are calculating. Otherwise, if you are given with average wind speed, you can directly substitute instead of u as well, right. So, we will see both the way how it is being calculated. So, to explain you this particular concept, this practice problem is taken. Estimate the annual energy production from a horizontal axis wind turbine with a 10 meter diameter operating in a wind regime with an average wind speed of 7 meter per second. So, d is given as 10 meter, u bar is given as average wind speed 7 meter per second. Assume that the wind is operating at under standard atmospheric conditions. Rho is given as 1.225 kg per meter cube and efficiency is given as 0.35. So, if you substitute here in rho w, right. So, what you would be getting is 1.225 into 2 by 3, d is 10 into 10 whole square into u bar is nothing but 7 cube. So, this particular value turned out to be 18.67 kilowatt. So, if you want to do it in annual production, then you supposed to multiply that with 8760 hour per year as well, right. Instead of second step, I did totally power output annually, right. So, turbine efficiency is 0.35 and annual is 8760 and then your PA is 18.67 kilowatt. So, if you calculate, it is turned out to be 57.25 megawatt hour, because we are calculating in terms of hours. Okay. So, this can be done, or if you want to calculate directly using the formula of the actual power, right. Actual power we know, right. So, how we define PA? So, your PA is nothing but this is based on average wind speed, right. PA bar is nothing but half rho A u bar cube of rho is 1.225, they have already given, into A is pi 10 square, because 10 is the diameter, pi d square upon 4 into 7 to the power of cube. So, if you calculate, so this is turned out to be 16.5 kilowatt. So, if you want to calculate power output, average power output, then efficiency 0.35 and the annual production in hours 8760 hours into whatever you got here. So, that is 16.5 kilowatt. So, it is coming around to be 50.58 megawatt hour. So, one can calculate this way as well, but you need to mention, right, based on which you calculated the annual power production. So, if you have already probability distribution function, you can substitute this formula, or if you are making an assumption that this itself a average wind speed, you can calculate in this way also. But remember, assumptions or any assumptions being made to be clearly told in for the way you are calculating the average power production. And then torque at maximum efficiency. So, there are two types of forces which are acting on the blades. One is circumferential force, which acts in the direction of wheel rotation, that provides the torque. The second one is axial force in the direction of wind stream. So, that will be contracted by proper mechanical design. So, the circumference force or torque can be obtained from T equal to P upon omega, right. So, what is P? P is power, omega is pi d n, d is diameter of the rotor, n is nothing but shaft speed, P is power, and actual efficiency eta is nothing but P upon P total, P total is nothing but total power. So, from this if you want to calculate P, P total into efficiency and P total power available is half rho A V cube or U cube. Then T is nothing but torque, which is equivalent to eta of 1 upon 8, because here T is told as P upon pi d n. So, we already calculated P is nothing but eta 1 upon 2 rho. So, this A I will write it as pi d square upon 4 into V cube divided by pi d n. So, pi get it cancelled, 1 d. So, n would be there. So, 1 upon 2 upon 1 upon into 1 upon 4, 1 upon 8 eta 1 upon 8 rho d V cube upon n. At maximum efficiency, then we already know it is 59.3% or your Cp is 16 upon 27. So, this T should be multiplied with 16 upon 27 to get torque at maximum efficiency. So, which is 16 upon 27 into 1 upon 8 rho d V upon n. So, if you calculate, this is 2 upon 27 rho d V cube upon n. So, if you want to determine simple power, right, then what is the formula to be used? Half rho A V cube. So, here the wind speed is given, that is V is given 18 meter per second, and then the rotor radius is directly given, which is 45 meter, and air density is given in this problem 1.23 kg per meter cube. This is simple calculation. So, if you want to calculate area, which is pi r square, which is pi into 45 whole square. So, you would get 62 meter square, and wind power is half rho A V cube. Half rho is given as 1.23, A is 62 and 18 to the power 3, then what you would be getting is 22,817 kilowatt. So, if you want to calculate the torque at maximum efficiency, whatever we have derived as a formula. So, this problem is taken to explain that. So, wind at 1 standard atmospheric pressure 15 degree. So, that means rho is 1.226 kg per meter cube, and velocity is V equal to 10 meter per second. We are supposed to calculate the total power density in the wind stream, and then the maximum obtained power density, the torque at maximum efficiency for considering the turbine diameter of D is nothing but 100 meter, and then turbine operating speed, right, operating speed is given as 42 RPM, revolutions per minute, for the propeller type wind turbine. So, before going into calculating the torque at maximum efficiency, there are two things we are told to calculate: the total power density in the wind stream as well as the maximum obtained power density. So, the wind power is half rho A V cube, that we know. The power density here is the P total upon A. So, you might be wondering, the energy density is nothing but energy upon volume, power density is nothing but power upon volume. It is not the convention followed in the same way. For even here in wind energy calculations as well as in membrane applications. So, the power density is defined as the total power upon area. So, what happens when you do that? Half rho A V cube upon A. So, this A get cancelled, what you get is half rho V cube. So, that means your power density is proportional to the velocity to the power cube. So, irrespective of your the size of the rotor and number and other characteristics, you will be able to compare the systems. That is why power density here defined as a kinetic energy flux. Kinetic energy flux. Why it is flux? It is divided by area, and also the power is nothing but rate of change of kinetic energy. This we have already seen. So, because of this reason, to compare systems irrespective of the rotor diameter. So, here power density is defined as the wind power upon area. So, then from this we would get to know the power is proportional to the wind speed raised to the power 3. So, if you use to calculate power density, then of rho is given as 1.226 and V is given as 10 meters per second. So, what you would be getting is 613 watt per meter square. So, what is the maximum obtained power? So, the maximum obtained power density is nothing but maximum power obtained, maximum P upon A. So, then we already have, that is of rho V cube, right. So, if you multiply it with 16 upon 27, then you would be getting. So, this is 8. So, 8 divided by 27 into rho is 1.226 into velocity is 10 to the power of cube. So, what you would be getting is 363.25 watt per meter square. So, this is the maximum power density one would be obtaining using this rotor diameter and not rotor diameter, because it is independent of rotor diameter, using the 10 meter per second velocity and air density of 1.226 kg per meter cube. And then torque at maximum efficiency, we have formula 2 upon 27, 1.226, rotor diameter is nothing but 100 and V is 10 to the power of 3. So, n is rotations per minute. Remember here minute is given, but other data the V is in meter per second. So, you are supposed to convert minute into second. So, that is why we are converting 60 second as 1 minute. So, 40 upon 60. So, if you calculate this, then what you would be getting is 12974 Newton, because torque is nothing but a force. So, what you get is in terms of Newton. So, then next practice problem would be on power versus height, right. So, here the wind turbine diameter is given as 25 meter and is placed on a 40 meter tower in terrain with the power law coefficient is given alpha, which is 0.18. Find the ratio of available power in the wind at the highest point of the rotor and lowest point, right. So, D is 25 and hub height or the tower height is given as 40 meter, alpha is given as 0.18, right. So, here we need to use the formula V upon V naught is nothing but H upon H naught power alpha. So, the height we supposed to know here, right. So, what is height? Height low and H low is nothing but, if you imagine, so this is hub, you have the rotor of like this, right. So, the rotor total diameter is given as 25. So, the maximum is here 12.5 and here 12.5, right. So, this height is given for us 40, right. So, the lowest height is this 40 minus 12.5, because this part comes down. So, which is nothing but 27.5. The height at high is nothing but 40 plus 12.5, which is nothing but 52.5. Okay. So, if we want to calculate the V upon V naught, right, then it would be H upon H naught. So, this is 52.5 upon 27.5. Low is we have taken as a reference. So, to the power alpha, it is 0.18, which is coming as 1.12. but that is not here asked. Here it is asked find the ratio of available power, right. So, we already know if we want to calculate the power, that is equivalent to the velocity to the power, because power is of a rho u cube. So, if both are same for two situations, if area and rho is same, then it is proportional to u cube only. So, P upon P naught is nothing but V upon V naught whole cube. So, which is equivalent to 1.12 to the power cube. What you get is 1.417. So, how the power is nothing but 1.417 of the power at reference. This ratio P upon P naught, which is equivalent to 1.417, is the ratio of available power in the wind at the highest point that rotor reaches to that at its lowest point. Then the second one is on how to calculate output power, right. Find the size of a wind turbine rotor that will generate 120 kilowatt of electrical power in a steady wind of 10 meter per second. Assume air density is 1.225 kg per meter cube and the power coefficient is given as 16 upon 27, eta is given as 1. So, eta is given as 1, Cp is given as 16.27 and velocity is given as 10 meter per second. So, we are supposed to calculate wind turbine rotor, right. So, then A is nothing but pi r square, but we do not know what is r. So, that is what we are supposed to find it out, and then the P out is given, P out which is nothing but 120 kilowatt. Remember the formula, the P is nothing but of rho A u cube kg per meter cube meter squared into meter squared upon second squared, right. So, this is coming as kg meter, rho is kg per meter cube meter squared. So, meter squared upon second square. So, what you get is kg cube meter cube upon second cube. So, cube get it cancelled. So, kg meter squared upon second cube. So, that means kg meter second square into meter per second, right. So, this is nothing but force into distance, which is nothing but the r, this is force into meter, Newton meter upon second. So, joules per second, that is power. So, remember this is given as joules per second is nothing but watt, right. So, your power is given as kilowatt, that one should be careful when you are substituting. So, P out is given 120 into 10 to the power of 3 watts of rho is given 1.225, area we do not know, pi into r square, and u is given 10 to the power of cube, mechanical efficiency is given as 1 and Cp is given as 16 upon 27. So, if you want to calculate r square, which is nothing but 120. So, this 10 to the power of 3, 10 to the power of 3 we can cancel it out. So, 120 into 2, that is in denominator. So, divided by 1.225 into pi, or 16 upon 27 is nothing but 0.593, right. So, this is nothing but r square. So, from this if you calculate r should be 10.2 meter. So, this is nothing but rotor diameter. And then the next and last problem of this course is calculating the rotational speed and then tip speed. The power coefficient already we defined and tip speed ratio also we defined already. So, this is sometimes you might require the Reynolds number, that is rho ul upon mu. Then mu upon rho is nothing but nu, which is nothing but kinematic viscosity of the fluid, mu is dynamic viscosity, L is the characteristic linear dimension and u is nothing but flow speed and rho is nothing but density of the fluid. So, here the problem given is 30 meter diameter 3 bladed wind turbine, right, produces 600 kilowatt at a wind speed of 12 meter per second, air density is given. We are supposed to find out rotational speed of the rotor at the tip speed ratio of 4, and then what is the tip speed in meter per second. So, a tip speed ratio lambda is nothing but r omega upon u. So, this omega can be used as this way as well. So, again the notation, the different books follow, right, you need not get confused. So, this also can be used. So, here the lambda is given as 4, right, and r is also given because here 30 meter diameter. So, then r is nothing but 15 meter, and u is given at the wind speed of 12 meter per second. So, what you are supposed to find out is omega. So, 4 into 12 upon 15. So, this will come as 3.2 radians per second, right. The second one, what we supposed to find it out is what is the tip speed, right. So, this particular thing is equivalent to 2 pi n upon 60, right. So, 2 pi n upon 60, which is omega, is nothing but 3.2 radians per second, and n is nothing but 3.2 radians per second upon 2 into pi. So, this is radians upon revolutions, because they asked in RPM, right. So, what we supposed to do it in minute. So, then we say 60 second upon 1 minute. So, radians get cancelled, second get cancelled. So, revolutions per minute. So, n is nothing but 3.2 into 60 divided by 2 into 3.14. So, what you would be getting is 30.55 revolutions per minute. So, this is first question, the rotational speed of the rotor at the tip speed ratio of 4. The second one is what is the tip speed, right. So, tip speed is nothing but lambda u, which is equivalent to r omega. So, r is what? R is 15 meter and omega is 3.2 radians per second. So, if you multiply 15 into 3.2, so it is 48 meter per second. So, that is all about wind tunnel performance parameters. So, the suggested reading materials and references are these for all these 4 lectures whatever I have done in wind energy. So, the first week we had basics and concepts, second week we had characteristics and the power extraction from wind energy. Apart from that, the wind energy can be used to pump the water as well. So, there would be few problems that will be solved by Professor Goud in continuation to practice problems whatever we have done today. So, with that I would like to conclude the course. So, this is basically a 8-week course. So, in that we covered solar energy, right, and then wind, and then biomass. So, we divided each module as 3 and then here 3 and then here 2, right. I started this course with solar energy. So, we had seen an overview of thermal applications, then solar radiation, and then we did practice problems. So, these are all about the solar radiation. Then second week of the course we have done the solar collectors, non-concentrating collectors, and concentrating collectors. So, and then we did practice problems. So, this is we have done for non-concentrating collectors. So, this concluded solar collectors for the second week. And then in the third week we started with solar storage system. So, in this we have done the sensible heat storage, and then latent heat storage, and then we have seen special case of solar storage and collection. So, which is nothing but solar ponds. And then in this particular week we also had solar energy utilization. So, in that we had two major category, one is on biomass energy systems and then wind energy system. So, here I introduced you the both concepts, how it is derived from solar energy, and then it was taken up by Professor Goud to explain the biomass energy rule, and then we both came back and started the wind energy. So, in wind energy we had types, terms, operating and design characteristics, and we both done practice problems, right. And this part was conducted by Professor Goud, so I do not have much idea about that. So, this is what we wanted to execute. We hope we could meet your expectations regarding this course. So, with this conclusion slide, I would like to thank Center for Education Technology head and office team, project team, and whoever involved with us in recording as well as editing for their help and support throughout the course. And then I would like to thank my co-instructor of this course, Professor Goud, for all the discussions and then support. And I would also like to thank my two TAs, Mr. Mranal and Ms. Swarna, for their help in uploading the assignments and preparing assignments and helping me in this course, for all the extended help and support. So, with that I would like to thank you for your patience throughout this course. And then if you have any further doubts apart from the discussion forum, you can write to both of us for any clarification, etc. Or if you are comfortable with TS, if you have some doubts, you can as well discuss with them. Thank you. Thanks a lot.